Okay, so now we have Sohn from the UCSF.
Thank you so much for inviting me to speak at this conference. I am a radiology resident, so I'm a clinician by background, but I also have some training in engineering, applied math as undergrad and master's degree student, and with some focus in machine learning. So I've been really excited about all the development of machine learning, both in computer vision and natural language processing these days. And I run a small medical deep learning research laboratory that we named Big Data in Radiology. So today I'll mostly talk about well, natural language processing, of course, and how it applies to radiology and why it's important, and vice versa. So maybe I thought it would be best to start off describing what radiologists do. So first and foremost, we are diagnosticians. We review medical images and then try to find some biomarkers in the medical images and communicate to the referring clinicians what is the diagnosis, what is the prognostic implication, and perhaps what would be a more favorable treatment approach. So that's probably our main job as a radiologist. But we're also a proceduralist. We perform image-guided surgery. Sometimes we drive catheter towards a liver cancer and then deliver chemotherapy right in front of the tumor. Sometimes we retrieve clots from the brain to treat acute ischemic stroke, and various other procedures that we do. And then finally, we are also medical imaging researchers. So we are at the heart of developing new CT technologies, new MR technologies, and also post-processing technologies like deep learning algorithms or certain types of 3D processing tools that are used in patient care. And I just want to make a little bit distinction between radiologists and radiology technologists. So we're not the people who are taking the images, but we're the ones who are interpreting the images and then communicating back to clinicians to add value. So we actually go through pretty extensive training after MD, 6 years of intern residence and fellowship training. And in some ways, one of the reasons why radiologists are not bachelor's degree trained or PhD trained is because we have to talk to the clinicians and talk about next steps. And in some ways, we are doctors, providing clinical value to the patient care. So that's why all the medical training that we go through. So I thought it would be best if I start off with a radiology case and just show you what we do and how NLP can be important in our field. So this right here is just a chest CT case of a patient coming in with hypertension and has a known condition called intramural hematoma, which is a life-threatening condition that can potentially lead to aortic rupture and exsanguination. So what we're seeing here is a cross-section of a chest of a patient. And this is the ascending aorta, descending aorta. These are the big blood vessels that come out of the heart and supply blood to the entire body, pulmonary artery here. And these are the lung parenchyma here, and then the entire chest wall over here. And what we see here is this sort of lucent-shaped hypodensity here around the blood vessel that signifies that there's an intramural hematoma, and this can be potentially really dangerous for the patient. So what I do as a radiologist in this case, we actually generate a text report to communicate to the clinician. So this report consists of various elements that are pretty standardized across hospitals and radiology. First component is, of course, the title of the study. We're doing a CT scan on the chest. And then the clinical history portion contains information from the referring clinicians about what's going on, why are we ordering this study, and then techniques about the study. So how are we obtaining the CT scan, and under what parameters are we giving contrast? And then we also give some radiation indication as well. And then finally, we go into the description of what we're seeing, and it can be a little bit convoluted and long, but compared to the general medical NLP literature, radiology NLP literature is actually much smaller in ontology and much more organized. So describing what's going on, describe the size and what we're seeing in the image. And it continues on to various body parts, various different organs, talking about the lungs, mediastinum, heart, and everything. And what happens afterwards is an important job of a radiologist that we actually explicitly get trained about, is generating the impression section of a radiology report. And what that entails is synthesizing all these descriptions of what's going on and then formulating into a concise yet comprehensive sentence that captures the crux of the image and then also sort of imbued with whatever recommendation here may be clinically relevant. So just to take a look at the first sentence over here, we're talking about the descending thoracic aorta intramural hematoma with some persistent intramural blood pool. And we're also explicitly talking about the supply from intercostal artery. And this is not a simple description of what's going on in the image, but we actually make an explicit decision to talk about the intercostal artery, because should the patient proceed to full exsanguination, the intramural hematoma gets bigger and then need emergency procedure, we as radiologists are recommending to take a close look at the intercostal artery, because that is the site of the bleed, and that's where to go for interventional procedures or surgery. So it's a very, very sort of elaborate sort of piece of a text document that we form as radiologists, even though the general sort of understanding from the public is radiologists are image analyzers, has nothing to do with NLP. NLP actually plays a very critical role in our workflow. So why NLP? In some ways, pretty similar to what I just discussed. Say we have a chest CT imaging right here, about 100 megabytes of data. What we see here is this sort of mass over here that's really concerning for lung cancer. So what I do as a radiologist, I start extracting relevant visual features, just like a convolutional neural network would do. Maybe it's compressed into about a megabyte of visual features. And then the next important job is to turn that feature into a very concise and well summarized description with my synthesis of what I think it is. In this case, it is something that's really, really suspicious for lung cancer. And in some ways, I've done just a 1,000-fold lossy compression of the data, extracting the most clinically relevant features to communicate to our clinician colleagues. And another reason why NLP is really, really important for radiology, let's just think about a case scenario where we're trying to be a computer vision engineer. So in this case, a medical imaging researcher. We're trying to train an algorithm that can automatically detect lung cancer from chest CT. We have this imaging data. It's going to go some sort of annotation to extract this most relevant area of concern in the image. But we also need to generate the ground truth label, the Y label that you need for putting into the TensorFlow or PyTorch, whatever algorithm, whatever library you're using. So to generate this label right here, the positive for this image, you actually need to go through these Radiology Report and then annotate these images. So this is where NLP comes in really, really handy. And anybody who's running a computer vision research team in radiology should know that NLP plays an important part. And that's why the NLP engineers are some of the best, could be best friends for this type of research team. And that's why in our research team, BD-RAD, we split our effort equally, half in NLP and the other half in computer vision. And finally, the third reason I think NLP is important in radiology, there's a lot of text data in radiology, not just reports, but communication between requesting physicians and radiologists, how we protocol our MRIs and CTs, and how we generate these impressions from these descriptions, and how to mine these radiation doses. So all these things are opportunities for text analytics in radiology. So again, these three important things, radiologist workflow modeling, ground truth generation, and text data analytics. So I've spent the past sort of almost 10 minutes talking about why this is important. I thought it would be good if I actually go into an actual project example of one of 6 projects that we're working on in NLP in BD-RAD and give you some example. So this is a project that was presented at the Radiological Society of North America, the largest radiology conference. And actually a student from UC Berkeley, Scott Warweth, did tremendous work on this project and contributed. So this project explores whether a radiology report contains a critical finding that needs to be called to clinicians because they may compromise patient care if not called in time. So some clinical background is when clinicians order a radiology study, then there may be some finding like big fracture, stroke, or something that's really time sensitive. And we as radiologists are trained to call them to make sure a patient gets the right care at the right time. But sometimes we do miss things, so it is helpful to have like an algorithm working by our side, saying you should probably call this case. Otherwise, patient's life or patient's health may be in danger. So why not train an algorithm that can read through the radiology report to determine this? And also from a department perspective, we can go back and audit all of our reports and see, are we doing a good job as a department to give call on time and also give call when necessary? But actually to engineering crowd, really, really important hidden motivation here is I want to create a lot of computer vision annotations. In some ways, each radiology report is associated with an image, a radiology image of a patient. And by annotating these positive findings, we are annotating the images as this is a positive image that contains an urgent finding. So that's sort of a hidden longer-term motivation that we have with this project. So we took about 200,000 data sets. At the moment, I guess it was anonymized, but institution A in this case is UCSF. Institution B is the Zuckerberg San Francisco General Hospital. And we used the UCSF dataset to train this algorithm to detect urgent findings presence. And then we also test the algorithm on the holdout dataset, as well as the external test set from ZSFG. So the actual technical implementation involves we extract the impression section of the radiology report that contains the crux of the finding, that the comprehensive sentence that's succinct, but also captures the key message of the report. And then we extract the ground truth label by seeing whether it was categorized as a report that had to be called. And this information, this is pretty well documented in the report because it actually has legal ramifications if we don't call at times when we are supposed to call. We do some basic NLP stop word removal lowercase. There's a few more additional very generic NLP pre-processing that we do. And actually, these sort of two last pre-processing are pretty unique to our project. Because there's a lot of cases where the impression mentions no evidence of fracture, no evidence of stroke, no evidence of something, or sometimes it even mentions no evidence of stroke or hemorrhage. It's really, really important to have a negative expression detector. And also sometimes radiology reports mention it may be stroke, it may be some other things, it may be depression, it may be heart attack. So in those cases, we assign a certain form of risk score so that the algorithm can take that into account as well. And then we perform semantic mapping, and Redlegs is a giant radiology term ontology library that we use to detect synonyms to make these exchanges, and it reduces our problem space. And I was really, really glad to see the previous speaker talking about clever technology. Our student actually brought this to our attention, and I wasn't directly involved in the implementation with the clever, but another sort of general medical synonym terminology that we use in our projects. So I was really, really glad to see that there's a lot of sort of work together. Okay, what happened here? So after these pre-processing, what happens is, well, let's take a look at this example here. We have the ground truth label here that there was a critical finding that needed to be called. And then we talk about, in this case, a colon wall thickening associated with some findings that are suggestive of diverticulitis, which is inflammation that may need to be, that may be surgical and may need the attention of the clinician. So in this case, we sort of substitute some of these terms, like descending colon was linked with this underscore to denote that they should be together. Because if you separate descending and colon separately, it may lose its meaning. And certain errors that it make too here. Let's take a look. For example, as was turned into arsenic. I think it's probably somewhere in the clever terminology or some other mapping that AS is turned probably recognized as the periodic table term arsenic. So it's like an error that it makes here. And then also, it also makes some negx term substitutions, and risk is our hedging detector that also makes these substitutions. So it generates a very, very succinct report that we can train the algorithm on. And again, the Redlegs, it's a really, really important ontology system for us. Available only in English and German at this point. So I don't think we can generalize this to all the other languages unless they develop their own version of Redlegs. but this allows us to reduce the problem space. And then for our model training, we took the model from Fast AI, a FAIR Facebook AI research team. This is actually the fast text model. We actually tried multiple different ones, SVM, convolutional neural network, and various other things. But this actually turned out to give the highest accuracy for the speed that it delivers, about 100 times faster than convolutional neural network. So what happens is we put in the preprocessed document, and then these word embedding vectors are intelligent word embedding system where, unlike Word2Vec or Glove, these are not actually set in place. So these are determined, these sort of almost like a neural network shaped model is set up here, and then it gets averaged and then gets into these a hidden linear layer. So it resembles a lot of what convolutional neural network looks like, but the activation function here is not a ReLU or 10H. It's a linear function, so everything summarizes into like a matrix multiplication, and then through backpropagation, it determines the best word embedding vector, and then trains. So, unlike most typical NLP algorithms, again, we don't actually set the word embedding. It's determined in an intelligent fashion. A lot of the details actually can be found in this Jolin et al. From the Facebook website. So we achieve these accuracies. So 0.90 AUC, 0.87 AUC in the external test set. Of course, when you get to external test set, there's a different population. So it's expected that there's some sort of drop in accuracy. Also, different institutions have slightly different preference on how we communicate and when we need to pick up the phone and make a phone call, whether urgent finding is present or not. So that led to sort of differences. And also, we had to conduct some error analysis, just review what's going on. And in many cases, actually, the ground truth label was incorrect. I would say about, I don't really report the result here, but I would say when I analyze about 100 cases, I would say about 90% of the cases, the ground truth label was incorrect. And I have to apologize, a demo. Actually, we have an online web version of this, but I confirmed that they made a change in UCSF firewall policy, and then unfortunately I cannot, it's offline at the moment. Sorry about that. But these sort of terms that are of importance, I agree as a radiologist that these are the terms that would be associated with a phone call that we have to make. So it's like a easy web module. And what I love about NLP is that unlike computer vision, the data set is smaller, and we can easily sort of just form this into like a online tool where people can just go in and experiment. Again, at the moment, the model is offline. But anyways, closing thoughts. Again, radiologist work involves both computer vision and NLP, and in some ways, I'm always looking for opportunities to learn from great NLP engineers at Berkeley, and to have people join our team. And we have weekly seminars talking about computer vision and NLP papers that come out in the BD Red. So I think that'll be a really, really nice opportunity. And again, I love NLP projects because they can be easily validated. So I want to acknowledge our BD Red research team and Scott Warwith, who put in a tremendous amount of effort into this project, along with some of the advisors in radiology, as well as the Baker Institute at UCSF, who's provided lots of logistical and theoretical support. If you have any questions, I'm happy to take.
Yes, so we have a couple of minutes left for questions.
I'm curious if this intelligent word embedding tool is that particular to a prediction task? Because I saw that you were going to positive and negative at the end. Mm-hmm. Is that the pipeline, or is it
Yeah. So it's something that changes over whatever the thing that you're trying to predict. So in some ways, that's what adds like a lot of flexibility and versatility. So yes. Mm-hmm.
I could imagine someone seeing the output of your, or should you look at this note, or should you go over this test or patient or not, but wanting to know what in that note was predictive of a particular yes or no. Do you have any of that?
Yes, I do. I guess the error analysis portion, which one is most highly associated, which word is most highly associated is exactly. And we actually, I guess we don't actually give this on this particular slide, but In the actual publication, we have almost like a waterfall type of plot that shows what is the most important word for each cases that predict positive or predict negative. So those words are reported indeed, yes. I think that's a really useful tool, in fact.
Can I ask another quick? How are you evaluating summarization? So for example, and I'd love to help you more because I know a student that just wrote a nice paper on this, but how are you evaluating the goodness of summarization? I know it was one of the tasks.
Yeah, unfortunately, we actually don't evaluate. We actually try to put in the findings section as well, but I think that results in just model just being really overcrowded. So it ended up being better to put in a small crux like sentence impression that went in there and then made the prediction. I do think just from being a radiologist and writing these impressions, a vast majority of these impressions do contain all the information needed to make that decision, because at least the classic teaching in radiology is that the impression sentences need to stand on their own and capture the entire comprehensive meaning of the report. But if you have any suggestions, I'm welcome, you're welcome to.
What they did was they showed it to clinicians, and there's the automated summary and then one that a clinician wrote, and 70% of the time the clinicians preferred the automatically generated one.
Oh, wow.
I'd love to hear,
Yeah.
what you might be doing.
Yeah, I mean, that is actually one of our other projects, is automatically generating the impression. This particular project just uses the impression that was already written by human, but in another one, there's a project where we use a neural machine translation to automatically generate the impression. It's not an easy task, as I explained, how the impression is generated, because it actually has a component of clinical recommendation and how we kind of get in the shoes of the clinician and try to predict what they want to do. Not an easy task, but I would love to get your insight on the technical, yeah, of course. Yeah, sorry if I'm taking too much time, but yeah.
I guess one last question. Thank you.
Yeah.
Thanks again.